Quantum Machines discusses direct digital synthesis for large-scale quantum computing. In developing the OPX 1000, a controller fit for the ever-growing quantum processors counting 1000 qubits and beyond, we had to think deeply about every detail that impairs scalability. Our recently unveiled OPX 1000 module for microwave generation, MWFM, generates pulses up to 10.5 GHz directly, without analog oscillators or mixers. The choice of technology to reach microwave frequencies is not trivial. We choose cutting-edge direct digital synthesis, DDS, for very specific reasons, and we believe it will enable scalability and performance to an even greater degree. In this blog, we dive deeper into the considerations for going this route and existing alternatives. So stick around, whether you like mixers or hate them. This will be an interesting ride. Summary of technologies for microwave operation. The control signals for qubit drive and readout often fall in the microwave range, which is outside the range of baseband controllers. Many qubit labs have solved the issue with solutions based on mixing, including single sideband mixers, IQ mixers, or more complicated schemes such as double superheterodyne, DSH, conversion. Mixer-based solutions make use of analog local oscillators, LOs, that are multiplied by the signal of a controller or an AWG. IQ mixers naturally suffer from two main spurs, affectionate name for unwanted signals, the low leakage and the mixer image, which require non-trivial calibration to be removed. Other schemes, such as double superheterodyne, offer a zero calibration solution but use many more components. Additionally, mixing schemes require having a low source per mixer if different drive frequencies are used. Having a low phase source per mixer is very expensive, and in order to cut prices, will probably include a phase lock loops, PLL, leading to phase differences between channels, which is detrimental for multi-qubit systems. In other words, while mixers can be useful, we need to be aware of the pros and cons involved. Direct digital synthesis, DDS, is a more recent technique with clear advantages over its analog counterpart. DDS allows for a much simpler system, with no mixture, no low, no calibration. A DDS-based solution gives a much better frequency agility, improved phase noise and overall precise control over the phase of even multiple channels playing synchronously. Here is a summary of how DDS compares to some alternatives, to be explained in the remainder of this blog post. A deeper dive on SFDR and bandwidth. The first performance indicator for microwave generation or up conversion modules is the spurious free dynamic range, SFDR. This tells us how much power difference there is between the signal we want to play and the unwanted signals, spurs, that happen to be generated. Because of low leakage and the generation of an image signal, IQ mixers require calibration for good SFDR. Quantum Machines Octave allows plug-and-play operation up to 18 GHz with an SFDR of 50 dBEC, although the calibration process is far from trivial. The Octave's fast and automated calibration process reduces some of the pain, but not without a price. Mixer calibration is usually narrowly centered around the calibration frequency, which is not great if one needs many frequencies, large bandwidth, or quick switching of frequencies. IQ mixing solutions require one mixer and one amplifier per channel, but also one low per channel if multiple frequency carriers are used. See setup in figure. Above, different methods of generating microwave for qubit control and readout, IQ mixing, double superheterodyne, DSH, and direct digital synthesis, DDS. More advanced schemes are engineered for high SFDR, such as DSH, and allow for up to 70 dBEC, narrowband, and 60 dBc on its operational bandwidth, only using filters and no calibration, at the cost of more components used. Instead, the OPX 1000's new MWFM module, operating with DDS without conversion or mixers, gets us an SFDR exceeding 60 dBc on the entire 0.05 to 10 GHz spectrum. DDS needs no calibration and offers ideal performance with much better phase coherence and fewer components, more on this later. The truth is that most QUIC chips won't see a difference between 50 dBc and 70 dBc. The fidelity of even the best currently available QUICs is impacted by all sorts of other sources of noise and spurs, from cross-coupling between channels, environmental noise, and more. Thus, the need for better SFDR saturates around 50 dBc, where you can be sure your control system won't be the fidelity bottleneck anytime soon. Follow this link to read about phase coherence and scalability considerations.